You know, when you crack open a fresh bag of your favorite potato chips and wonder why it's pumped full of all that, well, empty air? Or maybe you've walked past an old abandoned car and just marveled at how solid, heavy iron slowly turns into flaky orange dust over time. These aren't just random acts of nature. They are the physical evidence of a totally invisible world operating right in front of us every single second of the day.
Welcome to this explainer. Today, we are going to decode the secret language of the universe. We often think of chemistry as just, a bunch of arbitrary math and confusing letters on a chalkboard, but it's really not. It's actually a highly structured, brilliantly logical, symbolic language used to describe reality itself. And once you know how to read it, you're going to see the world entirely differently.
Okay, let's dive into this. Here is our roadmap for today. 1. The grammar of chemistry. 2. Combining and breaking apart. 3. The chemical swap meet. 4. Neutralization and redox. And finally, 5. Chemistry in real life.
All right, kicking things off with Section 1, the grammar of chemistry. To truly understand this universe, we first need to understand how it writes its sentences. Instead of clumsy words, we use equations. Think of it a bit like baking a cake. On the left side of our chemical sentence, we have the reactants. Those are your starting ingredients. We separate them with a simple plus sign and then draw an arrow pointing to the right side where we find our products. That's the completely new substances formed. Or, in our analogy, your finished baked cake.
But a good sentence needs some rich context, right? We add physical states in tiny brackets. It's essentially the universe's version of a highly concentrated text message. We use S for solid, L for liquid, G for gas, and AQ for aqueous, which just means dissolved in water. We even use up and down arrows to show gases escaping or solids falling out. And if we want to speed up or slow down a reaction, we just write catalysts, temperatures, or pressures right above that main arrow.
But here is where the really strict rules of grammar kick in. When we write out these equations, we often have to multiply the molecules to make absolutely sure the number of atoms on the left perfectly matches the right. So why do we go through all that trouble to balance an equation? The answer? The law of conservation of mass. This is literally a non-negotiable law of the universe. Mass cannot just magically appear out of nowhere, and it absolutely cannot disappear into nothingness. The exact number of atoms of each element that you start with on the reactant side must equal the exact number of atoms you end up with on the product side. We balance equations to reflect this absolute truth.
Moving right along to Section 2, combining and breaking apart.
So if elements are our vocabulary, what kind of actions can they perform? Well, first, they combine. When two or more substances merge into a single new substance, that's a combination reaction. A great example of this is adding quicklime to water. It violently forms slaked lime, bubbling and releasing a ton of heat. Because heat escapes, we call this an exothermic reaction. But on the flip side, we have endothermic reactions, which actually absorb heat kind of like a sponge. Now, those endothermic reactions, they're usually decomposition reactions, where a single compound is literally forced to break down into simpler substances. To rip those molecules apart, you have to pump energy into them. You can do this in 3 distinct ways: thermal decomposition, by absorbing heat; electrolysis, by passing electricity through something like water to split it into hydrogen and oxygen gases; or photochemical decomposition, where a compound, like silver chloride, absorbs sunlight and violently breaks apart into silver and chlorine.
Which brings us to Section 3, the chemical swap meet.
Now, what's really interesting about this slide is that not all elements play nicely together. Sometimes there is some real drama. Welcome to the chemical swap meet, which is basically ruled by a natural hierarchy. In a single displacement reaction, a highly reactive, aggressive element will literally kick a weaker element out of its compound. Drop highly reactive zinc into a solution of copper sulfate, and it just forces the copper right out, leaving you with zinc sulfate and isolated copper. It's pretty much chemical bullying.
But hey, sometimes it's actually a perfectly mutual, agreeable trade. In a double displacement reaction, 2 different compounds exchange their ions simultaneously. It's a complete partner swap. As we see here, sodium sulfate reacting with barium chloride, they seamlessly trade places to form barium sulfate and sodium chloride. Everybody gets a new partner, and the whole chemical equation stays perfectly balanced.
Let's shift gears a bit. Section 4, neutralization and redox.
You know, the universe absolutely loves equilibrium, and we see this perfectly when acids and bases interact.
When an acid meets a base, they engage in what we call a neutralization reaction, essentially canceling out each other's extreme properties. If you mix hydrochloric acid and a basic potassium hydroxide, they fight it out and leave behind nothing but completely neutral salt and pure water.
Then we have this entire hidden flow of electrons. Oxidation is the loss of electrons, while reduction is the gain of electrons. An easy way to remember this, just think Leo the lion says grr. Loss of electrons is oxidation, gain of electrons is reduction. And this perfectly translates to the addition or removal of oxygen and hydrogen too. They are exact mirror images of one another.
But here is the secret to this. They literally never happen alone. In what we call a redox reaction, which is just a mashup of reduction and oxidation, these two opposite processes are happening continuously, simultaneously, side by side. If one substance loses an electron or an oxygen atom, the other substance sitting right next to it absolutely has to gain it. It's a perfect, closed-loop transaction.
All right, let's bring it all home. Section 5, Chemistry in Real Life.
Let's take all of these abstract symbols and put them right in your driveway to answer our cold open question. This is corrosion. It occurs when reactive metal surfaces are attacked by air and water over time, rendering them incredibly weak. That rusting car, it's actively undergoing an oxidation reaction right in front of you. The iron is combining with oxygen and moisture to form rust, which has a very specific chemical formula, Fe2O3.XH2O. That orange dust isn't just decay, it's a fully balanced chemical product.
And what about our food? When the fats and oils in our food are exposed to oxygen, they oxidize too. This process is called rancidity. This chemical reaction literally changes the molecular structure of your food, causing it to spoil, smell bad, and just taste awful.
So how do we actually fight back against this? Well, we add antioxidants to fatty foods. We use airtight containers and refrigerators to slow the reaction rate way down. And that bag of chips from the beginning? That empty air is actually pure, unreactive nitrogen gas. Manufacturers pumped it in to forcefully displace the oxygen, preventing your chips from going rancid before you even open the bag. It's practical chemistry at its absolute finest. When you start looking at the world through this lens, you realize something pretty amazing. Chemistry isn't just something confined to a textbook or a dusty chalkboard. We are constantly interacting with the language of the universe. Every single breath you take, every meal you cook, every car engine that starts. The world is one giant, continuously balancing chemical reaction. You now know the grammar. You know exactly how elements combine, swap places, and oxidize. So I'm going to challenge you. Look around your room, look outside your window, look in your kitchen. What chemical reactions are happening around you right at this very moment? Keep your eyes open and never stop questioning the invisible language of our universe.